Hello. I'm going to, right now, talk to you about Avogadro's law and also gas stoichiometry. These are things which you can find in your book if you're watching this in spring of 2022, it's going to be on page 36. And if you're watching this, 35. And if you're watching this later than spring of 2022, then I don't know what page number it'll be on, but probably somewhere around 35, most likely. That's just sort of how these things tend to work out. All right, let's look at Avogadro's law of gases. Starting with, it's time for a thought experiment. Imagine there are two identical containers with identical numbers of gas molecules in them. The gas molecules inside each of them are all moving the same amount on average. Now, we know about gases that if things are moving the same amount on average, having the same amount of motion, that would be the same amount of kinetic energy on average. And we know that kinetic energy on average is a measure of temperature. So we're told that the amount of movement of the gas molecules inside these containers, we're being told that all these from container 1 compared to container 2, they are moving about the same on average. That means they have roughly the same temperature. So how do these containers compare for each of our gas variables? Well, as far as volume is concerned, how much space it takes up, we're also told that these are identical containers. So that means they take up the same amount of space. They're the same size. That means they're going to have the same volume. So we can say that container 1's volume is equal to the volume of container 2. For temperature, since temperature is a measurement of the energy of movement, a measurement of kinetic energy, and we're told that they're moving the same amount on average, that also tells us that the temperature of container 1 is equal compared to the temperature of container 2. And when we think about the amount inside, we were also told that the two containers have identical numbers of gas molecules in them. So that is the amount inside is identical as well, meaning our moles from container 1 and container 2 are going to be equal. If the volume is the same and the temperature is the same and the amount is the same, what does that tell us about the pressure? Which we have not been told anything about the pressure in this thought experiment setup, but we can figure out something about the pressure. We know that the molecules in container 1 have equal volume, temperature, and amount compared to container 2. This means that they're going to hit the walls of their container with equal frequency. They're moving the same speed and amount in a container the same size, and there's the same number of molecules in each one. That means they're going to hit the walls with equal frequency. When gas particles hit the walls of their container, that is what causes pressure. So if they're hitting the walls equally inside their container, then that also tells me that their pressure is going to be equal. So we can see, like, if all these molecules are moving the same amount, and there's the same number of molecules in each one of these containers, and the containers are the same size, they are going to hit the walls with equal frequency. And every time it hits the wall, that causes pressure. E for pressure every time it hits the wall. Let's try a second thought experiment. Imagine two identical containers with identical numbers of gas molecules in them. The gas molecules inside each are all hitting the sides of the container the same number of times on average. So how does this compare? Well, for our volume, again, we're told that these are identical containers. So that means that my volume must be equal compared with container 1 compared to container 2. The pressure, we're told they're hitting the sides of the container the same number of times on average. That's pressure. So the pressure must be equal. And the amount, we're told that they have identical numbers of gas molecules in them. That is the amount. So container 1 compared to container 2 must have equal amounts of moles or equal amounts of molecules in each one. If the volume and the pressure and the amount are all the same in container 1 and container 2, if those are all equal, then that means that they're going to also have to be moving at equal speed. To have the same size container with the same amount of stuff in there hitting the walls at equal amounts, the only way they can do that is if they're moving at equal speed. If one container has them moving faster than the other container, they're not going to be hitting the walls the same amount of times. So if they're moving at equal speed, that also means they have equal temperature. Interesting. We need to look at the next page. If you're watching this in spring of 2022, you're going to have to turn the page to look at the back on page 36. And let's look at thought experiment number 3. I wonder if you can guess how this is going to go. We're imagining 2 containers with identical numbers of gas molecules. So that is equal amount. The gas molecules inside are all hitting the sides of the container the same number of times. That's the pressure. So the container 1 and container 2, pressure has to be equal. And we're told they're all moving at the same average speed. So that's our temperature is also going to be equal. So what do we know about the volume? If we know that they're hitting the sides of the container at equal rates, and they're moving at equal rates, and there's the same number of pieces inside each container, that tells us that with equal pressure and temperature and amount in container 1 and in container 2, that tells me that my 2 containers need to be equal size. Pretend I'm better at drawing equal circles than I am. They're going to be moving at equal speed. They're hitting the walls with equal frequency, and that means the containers themselves, the walls, have to have equal size inside. Let's try thought experiment number 4. I'm sure by now nobody has figured out any sort of pattern or anything. There's definitely nothing to see here. We're going to imagine 2 identical containers. That tells me that their volumes are going to be equal. The gas molecules inside are all hitting the sides of the container the same amount of times on average. That tells me the pressures are going to be equal. And they are moving at the same average speed. That tells me the temperatures are going to be equal. Equal, equal, equal. The molecules in container 1, we know, because we've been told, they have equal volume, pressure, and temperature compared to container 2. This means that they will move at equal speed with the molecules in container 2. They're going to hit the walls of their identically sized containers with equal frequency, and that means the containers have to have equal moles. They must have the same amount of stuff inside. The only way we can know for sure that they're moving the same amount, hitting the walls the same amount, and inside the same size container, the only way that can work is if they also have the equal number of stuff inside. If one of them had more stuff inside the other, then the amount of times they were hitting the walls would be different, or they'd have to be moving slower to keep the amount of times they'd be hitting the walls the same. You can't have 3 of them equal unless the 4th one is also equal. And that is the point of this whole thing. Your bottom line, out of our 4 main gas variables, pressure, volume, temperature, and moles, if any 3 of those are equal between any 2 containers that you're comparing, then the 4th one also has to be equal. If 2 of them are equal, the other 2 may or may not be. But if 3 of them are equal, the 4th one has to be equal. That's the only way it works out. The 4th one has to be equal. Okay? let's look at the next page. If you're watching this in spring 2022, I'm now looking at page 37. Avogadro's law. At STP, the molar volume of a gas is always 22.4 liters. Here's what this means. Because I know that if three things are equal, the fourth thing has to be equal. I can say for any two containers, if they are at STP, you may or may not remember, that means standard temperature and pressure. I'm going to abbreviate a little bit here. Standard temperature and pressure. That is 0 degrees Celsius and what we call 1 ATM, 1 atmosphere of pressure. If two containers are at STP, so they're at the same temperature, 0 degrees, they're at the same pressure, 1 ATM, the molar volume of a gas, meaning they have 1 mole, how much space does it take up? 1 mole will always take up 22.4 liters of space if your container is at 0 degrees Celsius and 1 ATM of pressure. We know this to be true because it's going to be true for any gas, that if they're taking up, if you have 1 mole of it in a container and you got the container to 0 degrees Celsius and 1 ATM of pressure, the only way you could do all three of those things is if you had 22.4 liters as your size of your container. So in this example here, it asks, do argon and oxygen have the same number of molecules? Well, if I look, the volumes are equal, the moles are equal, the pressure is equal, and the temperature is equal. All four things are equal, and the number of moles tells me the number of molecules. 1 mole is 6.02 times 10 to the 23rd molecules. So do they have the same number of molecules? Yes, they do. How do we know they're both 1 mole? Then it asks, does nitrogen have the same number of molecules compared to argon and oxygen? Well, I can see, even though we're not told how many moles nitrogen has, I can see that it's got the same volume, pressure, and temperature compared to the other two gases. And I know if 3 of them are equal, the fourth one has to be equal. So does it have the same number of molecules? Yes. And how do I know? Because the pressure and the volume and the temperature were all equal. So the number of moles, which tells you the number of molecules, has to also be equal. Okay, then we have a data table. It says we have 3 samples, A, B, and C. There are 3 different gases, nitrogen, hydrogen, and neon. They're all at 273 Kelvin and 1 ATM of pressure. And then there's a certain number of moles depending on which one's which. So using the same table above, which 2 substances contain the same volume? Well, I know that if the temperature and the pressure and the quantity, the amount, the moles, if those 3 things are equal, the fourth volume would have to also be equal. So if I look, I can see equal temperature, equal pressure. For all of them, they're equal temperature and pressure, but only 2 of them are also equal moles, which means only sample B and sample C have 3 equal variables, temperature, pressure, and moles, or temperature, pressure, and moles, which means 3 things being equal, the fourth also has to be equal. Which ones definitely contain the same volume? It's got to be samples B and C. 3 things are equal, so the fourth has to be equal. If 2 different gases of the same quantity also have the same volume at the same temperature, what else has to be the same about the gases? Well, if 3 things are equal, we've been told here that the moles and the volume and the temperature are also equal. If 3 things are equal, the fourth has to be equal. So what's this also the same? It's got to be the pressure. The fourth. Okay. Any gas that is in a container at standard temperature and pressure, which is 0 degrees Celsius or 273 Kelvin, 1 atmosphere of pressure. Any gas that is in a container that has that temperature and that pressure, if you have exactly 1 mole of the gas in that container, it has to take up 22.4 liters. Your container has to be a 22.4 liter sized container. That's the only way you can get 1 mole of gas at those temperature and pressure conditions. This gives us a conversion factor where if I have a gas at standard temperature and pressure, then I can figure out how much space it takes up or how much of the gas I have. Here's what I mean. I'm given 2.4 moles of a gas. That's my given. They want me to find the volume. That's my unknown. I'm going to take that given 2.4 moles of gas. I know I'm pre-recording this video, but I can hear you groaning in my head. 2.4 moles of the gas. I'm going to convert it to find volume. They're asking me to find volume. It's my unknown, so that is a number of liters. And even if I don't know what number that is yet, I do know I'm going to need liters as my answer label. And because I'm so confident that I can solve this problem, I'm going to go ahead and draw an answer box with the word or abbreviation liters inside of it. I know that whatever my answer box label is, that has to be the last unit standing on top of my last fraction. So if I want to end with liters, I need liters to be on top at the end. And then my number of moles that I'm trying to convert away, I know that what goes up must come down. So if I'm starting with given moles, then I also need moles to be on the diagonal. That lets me cancel that out. Remember, any unit that's on top and also on the bottom can divide out. It gets canceled out. So we get rid of the moles. We're converting it to liters. And the conversion factor that we use here is that it's 1 mole for 22.4 liters. So I'm going to use 1 mole in my fraction. I'm going to use 22.4 liters in my fraction. And if I go ahead and do the math here, this really, in your calculator, is just 2.4 times 22.4. It comes out to 53.76 liters. And that's it. That's all there is to it. That's not so bad, right? There's a couple more practice here. I'm going to skip number 2 and look at number 3. Number 3 gives us 280 grams of nitrogen gas. That's my given. And they're asking me to find a size. So that's volume. That's going to be liters they're asking me for. So I'm going to take 280 grams of nitrogen, and I know I'm going to have to convert it with at least 1 fraction. Uh-oh, she said at least. What could that mean? I do know, look how much empty space she's leaving. That's sus. I do know I need my answer to be labeled liters, but here's the thing. I can only convert between moles and liters. I don't have a conversion between grams and liters, which means I'm going to have to take these grams, do what goes up must come down, and convert them to moles first. Then, if I have a second fraction, I could do what goes up must come down again to get rid of the moles, and that's when I can turn it into liters. So the moles and liters at the end are still going to be the 1 mole and the 22.4 liters. But I have to get moles first before I can actually finish the conversion of liters, which means I'm going to have to take those grams and turn them into moles, which means I got to use my periodic table. My number of moles is 1. Anytime I'm comparing it with grams, this says N2. So like nitrogen is 14.01, but there are 2 of them. So that's 28.02 for my number of grams down here. Can't believe we're doing fraction conversion factors again. Who could have possibly foreseen this coming? This does come out to, if you put it in your calculator correctly, 223.84 liters. Some of you may have noticed the title of the next page already. If you haven't, Well, here it is. Gas stoichiometry. Stoichiometry is back. It never went away. It was just hiding for a minute, but it's back. We're doing it. Stoichiometry. Remember, stoichiometry is when you're converting from one compound into a different compound using these conversion fractions. We just, now we have a way to do that with volume. So you can convert moles and liters this way. You may remember our handy dandy friend, the mole bridge. And if we look at this first problem, we're given 40 liters of HCl, a gas. So I'm going to do 40.0 liters of HCl. That's my given. This is going to be times some fraction. And then they're asking me to find an unknown hydrogen. So we're going to go from our given HCl into the unknown hydrogen. You thought you were never going to have to hear me sing that again. Sorry about you. We're going from the given chemical on the bottom into the unknown on top. And here's the beautiful thing. We always called this a mole bridge, but now at this time, I can tell you it is also a liter bridge. So you can do moles to moles with it, or you can do liters to liters with it. So I have liters of HCl up here. If I did what goes up must come down, I could put liters of HCl on the bottom. That is given on the bottom, and I can go into the unknown on top. And I can do that with liters to liters. This mole bridge can also be a liter bridge. It turns out they'll take liters from you too. So I can put the liters of hydrogen gas on top. And then for my coefficients, the 2 HCl in the coefficient, I can put in my fraction. The hydrogen does not have a number in front. When they don't put a number in front, they didn't actually write for you a coefficient. That tells me I can just use 1. So I'm going to use 1 liter of hydrogen here. And if we do the math, that comes out to 20 liters of hydrogen. Not so bad. So, okay, a liters to liters conversion, you can do that with 1 fraction. Because your mole bridge, it turns out, is also a liter bridge. You might even want to like write yourself a little note. Liters and liters for your given and your unknown. You can do that in 1 fraction. But spoiler alert, if it's grams and liters, you're going to need 3 fractions. So let's take, whoa. Awkward. Okay, let's take a look at that. With number 2. So we're given 4.61 liters of oxygen gas. 4.61 liters. Oxygen gas would be O2. I probably should have written this smaller because I already know I'm going to need 4 fractions. I'm going to run out of space. So I'm going to just like push this a little closer to itself over here. They're asking me for grams of KClO3, which means I'm going to need to use 3 fractions. And that's because I've got to convert liters to moles. Then I can use the mole bridge to go moles to moles. And then I can go moles to grams of the KClO3 so that I can end with this unknown grams KClO3 that they're asking me to find. So those grams of KClO3 that they're asking me to find can also go on top at the end because my unknown always goes on top at the end. And I know that what goes up must come down, so I can convert away the liters and liters of oxygen. If I'm changing chemicals, the only way to do that is with a bridge going from the oxygen into the unknown KClO3. It can be a mole bridge or it can be a liter bridge, but it cannot be a gram bridge. So I'm going to have to put that here, you could use it as a liter bridge here, but then you'd still have to have a third fraction to convert moles and grams anyway. So that's going to be like the messier way to do it. We're going to put our mole bridge on that middle fraction with the given 3 moles of oxygen given on the bottom, unknown 2 moles of KClO3 on top. Because if we do it this way, we can get out of here with the minimum number of conversions. So to get the mole bridge where it is, I have to recognize that these liters of oxygen I'm starting with need to be changed into moles of oxygen so that I could do what goes up must come down and put moles of oxygen on the bottom of that mole bridge fraction. When it's moles and liters together, we're using 1 mole and 22.4 liters, which we're allowed to do as long as the problem says it's at STP, because that's our molar volume with temperature and pressure conditions of STP. That you can use the 22.4 if they tell you it's at STP. That'll get us to the mole bridge. Then we can do what goes up must come down and cancel out the KClO3 moles. This is going to be 1 mole and your number of grams from the periodic table. So for K, that's 39.10. For chlorine, that's 35.45. And for oxygen, there are 3 of them. Each one is 16. So you're going to have to add that up. That's 122.55 grams going in my fraction. And then I have to put the whole thing through my calculator correctly, which there are many ways you could do this correctly. So you just pick your favorite. This comes out to, if you're rounding to the hundredths place, which you're supposed to in this class, always, all the time, 16.81 grams of KClO3. There you go. That is gas stoichiometry.